Okay, we're going to be talking about solubility equilibria today, and so we'll start off by talking about what a saturated solution is. Now, saturated solutions are something that we have talked about before, way back at the beginning of the year, and so just one of the things real quickly we need to remember that solutions are made of two things. We've got our solute and we've got our solvent. Solute is what's dissolved, and the solvent, not usually water, but not always, but it's going to be present in the largest amount. So we have two parts of a solution. Now, we can have different types of solution. We're just going to kind of focus on saturated solution for now. And so we'll draw a little model here. And this is a poorly drawn beaker with, let's say we have 100 mils of water in it. Okay, and what we're going to put into this beaker is we're going to put in here some barium sulfate, solid. And so we put barium sulfate into this beaker. We're having a nice pile of barium sulfate at the bottom, and we're going to get some of our barium ions ionizing, and we're going to get some of our sulfate ions ionizing, but truthfully not very many. By all intents and purposes, we would say that barium sulfate is insoluble. Not a whole lot of it dissolves, but we'll find out that a little bit it dissolves. Now, what we can have happen, and this is, let me just draw this, we have some barium sulfate remaining at the bottom of the beaker. So that's really what defines a saturated solution, is we do have this solution cannot hold any more barium sulfate. If I was to put more in, let's say I put 5 grams in, and it was at saturated, it can't hold any more, we would just make the pile of barium sulfate grow larger at the bottom. We wouldn't have any more ions in solution. It can only hold a small amount of ions. Now, one of the things that will happen is we can't have an equilibrium established. And so the equilibrium is that when we put the barium sulfate into the solution, our forward reaction is going to be the barium ions being produced as an aqueous form and the sulfate ions being produced also as an aqueous form. But and if I was to draw that on my model there, that would be going this direction. You would have these guys coming off of the barium sulfate solid into solution. Now we can also have this reverse itself and go to the left, where we have the barium ions and the sulfate ions recrystallizing back on the solid that's at the bottom of the beaker. And when the rates are equal, we know that we have a dynamic equilibrium. Now, because this can be shown as an equilibrium, we can always write a K expression for it. And so we're going to call this K expression KSP. And just looking at this expression here, the solid and the aqueous, when we write the KSP expression, remember we leave out our solids. So we're going to have the barium 2+, and we're going to multiply that by the sulfate 2-. And now this KSP is going to be called the solubility product constant, or KSP, solubility product constant. And what does that solubility product constant tell us? The magnitude tells us the extent of the solubility, meaning how much will dissolve. Now we can look up the KSP value for barium sulfate, and that's going to be located in Appendix D in the back of our book, and we find that that's 1.1 times 10 to the negative 10th. Because this is such a very small number, you know, it's 10 to the negative 10th, very small number, it tells us that our reaction definitely lies heavily to the left. So not a whole lot of the solid dissolves into solution. There is a small amount of barium and sulfate ions that do dissolve, but it really does lie to the left. We would say barium sulfate is insoluble, but a tiny little bit does dissolve. So if we are ever asked to look up a solubility constant, KSP, it's in the back of the book in Appendix S, or Appendix D, excuse me. Okay, I have an example here, and it's asking to write the solubility product constant for or KSP for calcium fluoride, CaF2. So the first thing I want to do is I'm going to write the net ionic equation. And so when solid calcium fluoride is placed into water, some of it's going to dissolve, so we have a calcium ion, and plus we have the fluoride ion. These are both going to be in aqueous solutions. Now, we do have to take it into account, and this is very, very important, that this reaction is not balanced. We do have 2 fluorides there, so we're going to have a coefficient of 2 there. Now, when we write the KSP expression, KSP, obviously we're going to leave out the solid once again, so it's going to be products over reactants. We're not going to have any reactant in it because it's a solid once again, so we're going to have the calcium 2 plus multiplied by the fluoride 1 minus. Now, because we do have the exponent of 2, we need to raise this to the second power. And there's a big mistake that students often make, is they forget to raise that to the second power, or when punching in values, they forget to square the fluoride. And so that's what we need to make sure we do. Okay, so throwing out a couple of definitions here that we'll be using quite often for the next few days when we go through KSP expression calculations and things like that, is the idea of solubility, which we kind of talked about it before. Now, solubility is going to be how much a substance will dissolve to form a saturated solution, usually measured in grams per liter. Okay, grams per liter. Now, solubility is different than solubility product constant. The solubility product constant is you write the K expression and you plug the values in at equilibrium, and then it's a unitless measurement. But with solubility, it actually tells us the amount in grams of something that will dissolve in per liter of water at a given temperature. Okay, the next thing is often comes up is the idea of molar solubility. And molar solubility is going to be the number of moles of substance dissolved per liter. Well, solubility itself is just going to be grams per liter. Molar solubility is going to be moles per liter. Molar solubility. So we can easily convert from grams of something that can dissolve in liters to moles by just dividing by the molar mass of that substance. Now I want to give you a little flow chart here that's going to help us run through, and we're going to be asked to run through 4 different things. And so here's our flow chart. Let's say we start with solubility. And again, like I just said, solubility is usually measured in grams per liter. And we could take that and easily convert that to molar solubility. And that's going to be in moles per liter. Easy conversion, all we have to do is convert grams to moles, dividing by the molar mass of a substance. Now, we can also take that and convert to molar concentration of ions. And to do that, molar concentration of ions, to that we're going to use stoichiometry. And we'll talk about that here in a few minutes. Then we can take that value and we can convert to KSP by plugging in the molar concentration of ions into the KSP expression, and then we have the KSP value. Now we can also take all these things and reverse them. We can go back this way, we can go back this way, and we can go back this way. And those are the things that we're going to be practicing in the coming days. So let's take a look at a quick problem that will allow us to use this flow chart. So, calculating KSP from solubility. So we have some solid silver chromate being added to water, and some of it remains undissolved. That's letting us know that this is a saturated solution. Analysis shows that the silver ion concentration in solution is 1.3 times 10 to the negative 4th molar. So just because they're telling us the analysis shows and we're just getting an ion, this is going to be our molar concentration of an ion. And so that's this part of the flow chart right here. And we're going to do a couple of things, and we're going to try to get ourselves to KSP. And so first off, we want to write the net ionic equation. So silver chromate, there's our silver chromate formula. and that's a solid, and we're going to break up into the silver ion plus the chromate ion. Both of these are going to be aqueous. And make sure I balance it. Yes, I got a 2 there, and so I'm going to put a 2 in front of my silver ion. Next thing I'm going to be asked to do is write the solubility constant expression, KSP. You can pause the video right here, right now, and try it yourself, and then check your answers. Okay, so KSP is going to be equal to the silver concentration raised to the second power and multiplied by the chromate, just like that. And the next thing we're going to do is we're going to calculate the KSP. Now we have to plug our values in here, and here's where it gets a little tricky. So it's not that tricky though. So if we're calculating the KSP, so it tells us that the silver concentration up here in the problem, silver concentration is 1.3 times 10 to the negative fourth. So I can just plug that in. So I'm going to have Ag 1 plus is equal to 1.3 times 10 to the negative fourth molar. That can be plugged directly in and then squared. But the chromate is different, because if we look at the balanced equation up here, we see that we have 2 silvers per 1 chromate. It's a 2-to-1 ratio, so we have to use a little stoichiometry. So what we're going to do is we're going to do 1.3 times 10 to the negative fourth for silver, and we're going to do some stoichiometry, and we have 2 moles of silver and 1 mole of the chromate. And you can see the value is going to be half of 1.3 times 10 to the negative fourth, which comes out to 6.5 times 10 to the negative fifth molar. So what we're going to do now is we're going to plug those 2 values that we have. We have our value for silver, we have our value for the chromate. We're going to plug them to the KSP expression. So we're going to go KSP is equal to our silver, 1.3 times 10 to the negative fourth. That's going to be squared, multiplied by 6.5 times 10 to the negative fifth. And so our KSP value for this silver chromate at this temperature is going to be 1.1 times 10 to the negative 12th. And that's a pretty small number, and so that tells us that, silver chromate is very insoluble. That equilibrium is going to lie heavily to the left. Okay, ladies and gentlemen, let's take a look at another problem here. What we have is we have a problem that's going to ask us to calculate our molar solubility of calcium fluoride, 35 degrees, and they're telling us that the molar solubility is 1.24 times 10 to the negative third moles per liter, or molar. What is the KSP? So what I'm going to do first is I'm going to start off by writing the equation. So we have calcium fluoride, solid, ionizing in water to form the calcium ion plus the fluoride ion. Noticing that there's 2 fluorines, so we're going to have a coefficient of 2 there. Okay. Basically, whenever we have a molar solubility problem, it becomes an ice table. And so let's go ahead and do an ice table for a molar solubility problem. So we have 1.24 times 10 to the negative third molar, just like we do on ice tables. And as you can see, this reaction's obviously got to go to the right. And so we're going to be adding plus x here. Trick is we have plus 2x there. And so obviously x is going to be 1.24 times 10 to the negative third. And then for the fluoride ion, it's going to be twice that. So we're going to have 2 times 1.24 times 10 to the negative third. And so on my equilibrium line, we can go 1.24 times 10 to the negative third, and then twice that is 2.48 times 10 to the negative third molar on both of those. So now we have our equilibrium line, and we can plug those values in to the KSP expression. So once again, our KSP expression was the calcium ion multiplied by the fluoride ion squared. So that's going to be equal to 1.24 times 10 to the negative third multiplied by 2.48 times 10 to the negative third squared. And so our KSP should come out to be 7.63 times 10 to the negative ninth. as a value for calcium fluoride at 35 degrees. And that'll be the end of tonight's lecture. We'll do some practice tomorrow in class.